as Professor Jurodov just sent us a message that he is not feeling well, and therefore he cannot come today. And therefore, we're going to reschedule his talk probably to the later part of the conference. So as the last-minute replacement, so I just, in order not to leave the time slot empty, so I just maybe spend about 15 minutes to tell you what we have been doing here. And I'm sorry to shortchanging you because I know very well that I'm only half the size of Nikolai. So as I'm only half the size of Nikolai, so I'm going to talk half the time that you're going to take, so only 15 minutes, okay? And so today I'm going to say something about Dirac cones and zero index, okay? And so in fact, let me use this slide to acknowledge my collaborators. In fact, most of them are in the audience. And now, most of us probably are aware that the so-called Dirac Cone dispersion can be found in the graphene, which is one single layer of graphite. And with this very peculiar dispersion, you can get a lot of very interesting physics. For example, this jittering motions, Wavefunction, Klein tunneling, quantum Hall effects. Of course, graphene can be used as a platform for a plasmon. And but this type of very single dispersion is not unique to graphene. In fact, they can be found in two-dimensional photonic crystals. And this was, in fact, quite well known to people doing photonic crystal calculations. And I think this paper was aroused a lot of interest because they saw that if you get a Dirac cone for photonic crystal, it's a classical wave, and then by breaking symmetry, time reversal, and so on, then you can get a lot of interesting phenomena. For example, you can have one-way edge states, and this aroused a lot of interest. Now, but today I want to talk about something else. I'm not going to talk about Dirac cone in either graphene or photonic crystal, because typically in these systems, you find the Dirac cone at the zone corner, okay, at the K point. I want to see if I can get a Dirac cone at the zone center. And this is not so easy because it happens that either for graphene or for photonic crystals or for phononic crystals, it turns out that if you have a hexagonal or honeycomb lattice, you are almost guaranteed to have a Dirac cone at the zone boundary, at the K point in particular, because that actually comes from the lattice symmetry. But however, for the case of the zone center, in fact, symmetry does not help you at all. In fact, if you do not have extra degeneracy, because of the zone center, as long as you have time reversal symmetry, the bands will be parabolic. But in order to get a Dirac cone, a necessary condition is that you must have linear bands. And therefore, it's not that easy to get a Dirac cone at the zone center, because if you have parabolic bands, you cannot have a Dirac cone. And now, but however, let us take a look at a very simple example. And I'm looking at a 2D photonic crystal making up of dielectric rods, okay? And of course, doing calculation for these are very straightforward. And you would typically get a band structure for the low-lying bands that look something like this for these type of structures. And for the low-lying bands, they come from the monopole and the dipole excitation of the cylinders. Of course, they interact with each other, they disperse and becomes a band. And this is a case in which this is monopole, this is dipole. And if you reduce the cylinder radius a little bit, you will find that, in fact, the dipole and monopole switched position, okay? And you can imagine that by tuning the radius, while keeping other parameters the same, there will be one particular system parameter, in this case, the radius of the cylinder, so that the monopole and dipole become the same frequency. Now, this is not something that is required by the symmetry of the lattice, but something that is by design or accidental. But if you happen to be that, you can see that that something interesting happens, because normally the bands will be parabolic at the song center, k equals 0. But if you have accidental degeneracy, then the bands becomes linear. And in fact, it can be shown analytically that in fact these linear bands generate some Dirac-like cones for you, and these in fact generate a cone. And just to give you some visual image of the states, if I look at the states near the zone center, if I point to refer this side, and you can see that the states in fact have monopole and dipole character. Okay. Now, and so it gives you a more complete band structure. And this is, again, 2D photonic crystals making of cylinders. And you can see that for this particular epsilon, which is quite reasonable, square lattice and hexagonal lattice, for both of them, you just arrange the cylinders in a square or a triangular array, then you get these linear bands. And this is a 3D plot to show you that we do get these Dirac-like dispersions, which is namely 2 cones touching at one point, plus 1 extra suite of bands that is very dispersionless. Okay, so I do get these Dirac-like cones there. And I can actually give you a design condition. That is, if we use what we call multiple scattering theory, okay, which considering the scattering of each individual cylinder and see how they come together to form a band, then it can be shown that if the so-called lattice sum is equal to the inverse of the scattering matrix of coefficient of the monopole degree of freedom, in fact, this gives you the condition for having a state for monopole dispersion. And if that happens to be equal to the inverse of the scattering coefficient for the dipoles, then I can assure you that you will get a Dirac-like cone. Okay. Now, now the d plus and minus 1 are equal by symmetry, but however, the d0 and d plus minus 1, namely the monopole and dipole, they are separate and independent degrees of freedom. They don't have to be equal, and in general, they are not equal. Okay. So you have to choose system probability that happen to be equal, and I can assure you that if they are equal, then you will get a Dirac-like cone. And now, and then I would like to say that these cones are in fact related to a zero index. And let me argue in the reverse manner. Let me suppose that I happen to have a epsilon equal to mu equal to 0 system, and I will argue that then you have Dirac cone dispersion. Now, why is it the case? Let me imagine that I have, for some reason, just by luck or whatever, I have a material homogeneous, okay, in which epsilon is almost or equal to mu, okay, and I assume that this material happens to have a 0 index, that is both of them equal to 0 at one frequency. Now at that frequency, the density of state for the transverse modes is 0. However, anything that behaves like this must be dispersive, meaning that at a frequency higher than this, you should have a positive index, because in that case, both epsilon and mu should be positive. While if you have below that frequency, the refractive index should be negative. Now, in those cases, the group velocity should be either positive and negative, just slightly above and below this peculiar point. Now, more than that, in fact, if epsilon and mu equal to 0 right at that point, you can be shown that, in fact, the group velocity must be finite. It's not 0, it's finite. Okay. Now, if you combine all these together, and then you can very quickly convince yourself that the dispersion have only one possibility, that it must be 2 cones touching at one point. You have no other possibility, okay? And therefore, you will see that if I happen to have a homogeneous material with epsilon equal to mu equal to 0, then I must have a Dirac cone. Now, so this is, in fact, more straightforward. But however, if I want to turn this around, and I want to say that suppose that I have some material which is discrete, composing of discrete resonators. And I would say that if I have a Dirac cone, now is it equivalent to epsilon mu equals 0? Now this is not obvious, because this is just, this implies that doesn't mean that the reverse is true, okay? And so, and then what happens is that if I have a discrete system, for example, a photonic crystal or maybe metamaterial, if I happen to, by design, my system have a Dirac-like cone, if I want to say that, or claim that it behaves like a refractive index equal to 0, then what is missing in between must be some kind of effective medium theory. And therefore, for the kind of system which is photonic crystal cylinders, and indeed the effective medium theory has been known for a long time, and therefore we just plug the system parameters into this very standard effective medium systems, and we found that, hey, indeed, we found that the effective epsilon and mu are indeed equal to 0. But I want to say something that is, if I get such a dispersion, it may or may not imply that I have a 0 index. That works only if the dispersion comes from monopole and dipole, okay? And it can be proved that is the case. If you have quadrupoles, for example, then the mapping doesn't work anymore, okay? And now, of course, has been known for many years that if you have a refractive index 0 or almost 0 material, you can have a lot of interesting wave manipulation possibilities. For example, you can have wave tunneling through waveguides. I think one experiment is done by Smith group. And it can also be used as a wavefront transformer. This is proposed by Professor Szyrakowski many years ago. And here I just want to show you that the photonic crystal does behave like a 0 index. And on here, I just show a hypothetical system, which we just put in the COMSOL numerical package, that I have something that is homogeneous, epsilon and mu equal to 0 plus a tiny bit of absorption. And you can see that the system behaves like a wavefront concentrator, a concentrator wave. And this is the photonic crystal with Dirac Cone, and you can see that by and large it behaves like that. And here we try to do an experiment with microwave, and so we put cylinders in, and it just happened that we cannot buy easily cylinders that have epsilon equal to 12. We end up buying cylinders with epsilon 8.8, so we have to redo the calculation. And the effect is not as good, but you can more or less see that this is a real experiment, this measurement. You can see that the effect can be verified. And this is a rather stringent test. So I now do a numerical calculation in which I have a channel, a waveguide, in which I put in a hypothetical epsilon equal to mu equal to 0 medium here. And in the middle, I have a void, I have a hole. And inside the void, I put in a metallic object there. And then I do a numerical calculation, pass a plane wave through this, this medium, and then see how wave should transmit. And the solid line is what the numerical package gives me. And so the transmittance can be almost 1 or can be almost 0, depending on the size of this metal stop and distance between the metal and the air gap and so on. Now this solid line is for a hypothetical homogeneous n equal to 0, while the dots are the simulation if I replace the hypothetical system with a real photonic crystal, the numerical calculation. And you can see that they actually track each other very well, so that this photonic crystal does behave somewhat, in fact, very much like a 0 index media. And now this is an experiment, it's not a simulation. So we put this photonic crystal and let it surround a particular metal barrier there. So we are basically trying to do experiment for one of these points in which we expect almost perfect tunneling. And and these are measured data of microwave at about 10 gigahertz. And so this is the case in which I have a bare metal barrier object there, this obstacle, with no photonic crystal, just air. And you can see that when microwave goes into the channel, I leave a shadow there, which is a shadow of this, this metal block. But if I surround the metal block with this photonic crystal with a Dirac cone, then you can see that the wave, plane wave, pretty much tunnel through. This again, let me emphasize, this is not a simulation, this is an experiment. And so actually some people call this cloaking in the literature, okay. And so it does behave like a 0 index media. Now, the nice thing about classical wave is that you can do a lot of things that electrons cannot do. Now, for example, the concept of the Dirac cone is manifestly that of a periodic system. It is almost meaningless to talk about Dirac cone in a system that's not periodic, because you have to have a band structure because you can talk about this Dirac Cone concept. But however, for photonic crystals, I can build a photonic quasi-crystal, which is not periodic, okay? And now, if the effective medium makes some sense, then it means that the system does not have to be really periodic. I can have non-periodic system. I should see the same effect. And this is a example of that. So I choose a quasi-crystal, like, in fact, a 12-fold quasi-crystal, which is not periodic, but in fact, a quasi-crystal. And then the parameters are chosen so that in the effective medium sense, you can do a simulation. That is still behave like a zero index. So does it work? And this is a numerical simulation, and this is an experiment, okay? This performed, and these are very new results not published yet. You can see that by and large, that when you put the obstacle in, the wave still tunnels through. So it is pretty much like the case when I have a periodic system. And so it allows us to extend the concept of the Dirac Cone from a periodic to a system that's not even periodic. Now, what is being shown here is the calculation done by Professor Dong Jianwen, one of our collaborators group in Zhongshan University, and what they did is that they put this photonic quasi-crystal in a large supercell. Now, of course, anything that's periodic is not quasi-crystal, but if you choose a big enough unit cell, huge enough, then they should approach each other. And what he did is that he put in these 12-fold quasi-crystal in a bigger and bigger unit cell. And this is not something schematic. It's really a band structure calculation for this huge unit cell. And you can see that when he put this in, you can see that the Dirac Cone refuses to die. Okay. It is still there, okay? But as the system gets bigger and bigger, you get more or less these flat bands. And these are, in fact, localized ring modes that are specific to quasi-crystals. And these are localized modes. They don't propagate energy for you. But still, you have these cones that refuses to go away. And so you can see that this concept is, in fact, quite robust. Okay. Now, I want to emphasize, because quite a few colleagues asked me, is that is there any difference between a single zero, meaning that now for a refractive index to be zero, the n square is equals to epsilon times mu. So you only need one parameter to be zero. So is there a difference between only a single zero or a double zero? Now, I would say that there are differences. Now, for example, most of the single zero material that, for example, if only epsilon is zero to get a zero index, they typically are done using metals. Now, in the photonic crystal case, this is entirely dielectric. Okay, and so I think at least there's one advantage, is that if you have pure dielectric system, you have less loss. And therefore, the pathway to go from a low frequency to a high frequency is probably easier than if you employ metals. There's also a difference because, strictly speaking, if you have a zero index with only one of them equal to zero, and then, in fact, the group velocity is zero. Okay. But however, if both of them is zero, the group velocity is finite. Okay, it can be proved that way. So you may have some advantage in that sense. Now, but however, I do want to say that what we have now is a photonic crystal that gives you a Dirac Cone. But this Dirac Cone have a lot of different properties from a Dirac Cone that you find at the zone boundary. Now, for example, a lot of physics, interesting physics of the Dirac Cone at the zone boundary because of this Berry phase of being pi, which is not zero, not 2 pi. But however, at the zone center, it can be proved that the Berry phase is always zero. And there are some very subtle reasons for that. Now, I also want to say that classical wave system allow us to, in fact, expand our concept in cases in which electrons cannot do. For example, the Dirac Cone for graphene is manifestly a 2D concept. Makes no sense to talk about a 3D Dirac Cone for an electronic system. And now, when we say that, what do we actually mean by a Dirac Cone in 2D? What it means is that we have this very peculiar dispersion, so that the E-grid frequency surface is a set of circles, which radiuses shrink linearly until it reaches zero and then expand again symmetrically. So if I want to extend this concept, so-called Dirac Cone, from 2D to 3D, Actually, what I mean is that can I find a system in which the equally frequency surfaces are a set of spherical surfaces, circles, so that the radius of that circle shrink linearly until it reaches 0, and then expands symmetrically again when you pass through that so-called Dirac frequency, so that these circles are being replaced. These circles are being replaced by spherical surfaces. Now, can that be done? Now, actually, and then you say that, well, suppose that it can be done. So what? Okay. At least there is one advantage, because for the 2D photonic crystals I've talked about that have a 0 index, it is still a system that's not isotropic. I'm talking about 0 index only if I confine my k vector on the 2D plane. Now, suppose that if someone wants to have a 0 index as an isotropic material, then in fact, what you require is this 3D Dirac Cone. Now, the question is it possible or not for a classical wave? Now, in fact, while we are thinking about this problem, Professor Sakoda from Japan already published a paper to say that it can be done, okay, using group theory. And he proved that if you have someone can find a system with a A1G and T1U mode, and forget about this. It basically means that you have a dipole and monopole. In that case, you can get, if you arrange them to be degenerate, you can get a 3D Dirac Cone. But it's not so easy, because it happens that for 3D optics, it's very difficult, if not impossible, to find a monopole for EM wave. And so we choose another way. In fact, it can be proved mathematically that if you happen to have degeneracy of electric and magnetic dipole, then you can, in fact, have a 3D Dirac Cone. But because my time is up, and therefore I won't go into details, and I just want to show you one extra slide, which is, in fact, very interesting. Because you know that a lot of attention are now being focused on topological insulator, and the attraction of there is that I can give you a piece of material, and they have very robust surface states. Okay? And it turns out that these Dirac Cone stuff can also give you very robust surface states, but for entirely different reasons, because of the fact that they can map to effective medium. And we know that if you have effective medium, they're positive and negative on one side and the other, you can have surface states. It turns out that this mapping, in fact, work very well, in fact, work better than I think. And in fact, they can give you photonic crystals in which one side and the other side are basically two sides of the Dirac Cone, and then we can always see surface states in the gap, whether you have a square or you have a triangle, they are always there. But I think I should not spend too much of our time, and let me just summarize by putting up my last slide here, and I will stop right here. And thank you for your attention.
So before we do any questions, let me get the next speaker coming up and setting up.
Was it you?
So it's Xining Zhu. Okay. So we have questions for CT.
Yeah, that's a nice idea. By making the magnetic and the electric dipoles degenerate, you can get this mu equals 0 point. Since you generally manufacture those dipoles in very different ways, that might be a little tricky. And so there's an alternate suggestion that if you have a chiral resonance, okay, which has a certain spin to it, and then you make a racemic mix of left and right-handed chirals, then that's easier to do, because you just make the mirror image of one, and I think it will have the same effect. I wonder if you agree.
I do.
Thank you.
And thank you for the comment. Yeah, I do agree.
One more.
CT, what do you mean precisely when you say it must be monopole plus dipole, no quadrupole allowed? Is that a strict statement that the quadrupole term is exactly 0, or just small compared with the other two? Small. Okay. And how
in fact,
small?
to get the Dirac Cone, it does not require monopole and dipole degeneracy. It can be obtained by other degeneracy. For example, you can have a quadrupole dipole, you can still get a Dirac Cone. What I mean by that is that if I want to map it to effective medium, the mapping works only if the degeneracy comes from monopole and dipole.
So we'll stop there and maybe save questions for the discussion.
All right. Thank you. First, I'd like to thank CT and John for organizing such a very exciting workshop. I'd like to talk a bit about some of our recent work concerning time reversal symmetry breaking inside nanophotonic structures. And these are the work from a graduate student of mine, Ke Jiefang, a postdoc of mine, Zhongfu Yu, and part of the experimental work was in collaboration with Hugo Lira in Professor Michael Lipson's group in Cornell. So part of our work are practically motivated. And there's a lot of interest in creating large-scale communication network, of course. And if you look at a communication network, one of the important component is the isolator. And there's also a lot of work in trying to integrate these kind of information network on chip for computing purposes. And for that purpose, of course, you would like to integrate many of these devices into an on-chip setting. And one of the important devices to integrate, therefore, is the isolator. So there are certainly conventional optical isolator available, and you can buy it, and they look something like this. Now, they use something called a magneto-optical effect. And one of the very important points about these effects are that it's non-reciprocal. So as a demonstration, this is something, for example, many of these isolators use an effect called Faraday rotation. So suppose you have a structure with a magnetization, then light that's propagating, co-propagate with magnetization will get its polarization rotated. And to see that this is non-reciprocal, what you do is you do a time reversal operation of the outgoing light. You send it backward, so it now counter-propagates the magnetization. And it does that. If it's non-reciprocal, it does not go back to the original state, but it further rotates. And so if you can do that and demonstrate non-reciprocal effect, then there are ways to convert this into an isolator. So the basic difficulty is that many of the standard magneto-optical materials are quite different from, for example, silicon photonics platform. On the other hand, most of the standard optoelectronic materials that one encounters, silicon, gallium arsenide, and so on, does not have magneto-optical effect. So from this, there has been a lot of interest in trying to create non-reciprocal effect without going through magneto-optics. Now, to do that, I think it's very important to reiterate a very old piece of statement that says any electromagnetic system that's linear, time-independent, and has a symmetric permittivity and permeability tensor, including medium that has gain and loss, in fact, are all reciprocal. So in fact, you could never create an isolator using a large range of standard optoelectronic material independent whether you put gain or loss into these systems. Now, this is sufficiently old, however, that it's important to actually reiterate this point. Now, one of the important points about any reciprocal system is that it has a symmetric scattering matrix. And so suppose, for example, if you have a 3-port network, and you look at the transmission coefficient from here to there, and you look at transmission coefficient from here to there, if you were a reciprocal system, these two transmission coefficients has to be equal in both amplitude and phase. Okay? And that basically, if you need to create an isolator structure, you need a non-symmetric scattering matrix. So this is very old, but I think, unfortunately, I guess, there's a constant source of confusion, so I want to, late in the afternoon, I try to at least give you one example that you can see this confusion. So here's the structure that we actually designed, a photonic crystal structure. Now, it has an aperiodic pattern in there, so the dots here are the silicon rod. And so if you send light from the left, you have very high transmission. And if you send light from right, you have low transmission. Okay. So before you get very excited about seeing this as an isolator, it's very important to point out that this apparent contrast intensity transmission from left to right versus from right to left, in fact, has nothing to do with optical isolation. In fact, has nothing to do with optical isolator. And in fact, the simple point to realize, of course, is you notice that the outgoing mode here is odd mode. So if you need to test non-reciprocity, what you need to do, you cannot send this mode back. You would need to send this mode back in. And if you do that, of course, there's no magic. You send the odd mode back, and you have high transmission going backward direction. Now, to get a more elaborate example, you can take a look at a comment that I recently wrote about a science paper that essentially made precisely this kind of isolator structure. So to reiterate, at least the first point, and I think you'll come back to the standard magneto-optical effect, is that the simple way to test is simply to time reverse the output mode. Okay? And also, again, to reiterate, if you need to achieve optical isolation, actually the choices are rather limited. You can do magneto-optical effect, and that's the only effect that's available for stationary structure. You can do nonlinear effect, and many people did that, but it only occur within the power, usually only occur within a small power range. So what we have been pursuing is a third option, and this is time-dependent system. For example, a modulator. And using modulation to break time reversal symmetry or break reciprocity is in fact well known. You actually buy it in commercial fiber gyroscope, but the important question is how to use that to achieve optical isolation. So what we show here in the past few years, what we've been pursuing is to use these dynamic modulation to replace magneto-optical effect. And the underlying piece of physics is something called photonic transition, as induced by dynamic refractive index modulation. So what we would like to show is that if you take a standard silicon waveguide and you modulate it in a very special way, then you can get frequency 1 to come in, to go out, and frequency 2. And if you send this frequency back in, you break time reversal, so it doesn't go back to the original frequency. And in doing so, you can actually create an isolator. So the idea of photonic transition was first developed actually by my PhD advisor, John Janopoulos, about more than a decade ago. And the point is that if you take a crystal or you take any photonic structure and you modulate the dielectric constant both as a function of time and space, then you can couple different states in this photonic crystal structure together. So you can start with this state, and it will oscillate into this state and come back if you choose the modulation right. Now, this actually has been experimentally seen by Michal Lipson's group in Cornell. One of the very interesting points that we realized, though, is that this kind of modulation in general is highly non-reciprocal. So as a simple example, if you take a silicon waveguide that supports 2 modes, an even mode and odd mode, you can then couple these modes together by basically modulate a section of the waveguide with a pre-described frequency and wave vector. And in doing so, you can couple the fundamental even mode to the first order odd mode. And this is how it looks like. You send in a fundamental even mode in here with a frequency ω1. Upon passing through the modulated region, it gets converted into an odd mode with a slightly higher frequency. Now, the interesting point about this modulation is that it simultaneously breaks time reversal and spatial inversion symmetry. And you can see that by simply taking the modulation pattern and flip either time or space, and realizing that if you flip either one, it actually does not go back to the original modulation pattern. And that's, of course, crucial. Being able to break this symmetry is, of course, crucial in order to get isolator. So as a result, this kind of modulation, while phase match 2 mode in the forward direction, in fact does not phase match any mode in the backward direction. So in the forward direction, you have a conversion, whereas in the backward direction, no matter what mode you send in and what frequency you send in, no conversion actually occurs. And the contrast between the first and the second panel here is a direct proof of lack of reciprocity in the system, because you basically send the outgoing mode back in and see that it does not go back to the original. And I would like to emphasize that this is a fairly broadband effect. The bandwidth where you can get isolation is in fact much larger compared with the modulation frequency that you put in. And all you need is basically to have 2 parallel bands and have group velocity matching. So that's the theory that we've done. Now, the other important point that I also would like to emphasize is that it's a linear device. It's a device that's independent of the data format, the amplitude, and the phase of the incident light. And that's, of course, crucial if you ever need to actually use isolator inside a system. So that was the theory that we did 4 years ago. And this year, in collaboration with Professor Michal Lipson's group, we actually have done a experimental demonstration. So this is what Michal did, what her group did, essentially, is to build a very large modulator. And the modulator region, waveguide region, is about 1 centimeter long and consists of 88 independently modulated regions. And so the idea is to control each individual modulator in just the right way so that you can create the right modulation pattern. So the optical part of the structure basically consists of a waveguide through a multimode interference filter coupling to a 2-mode waveguide and then coupling back into the single-mode waveguide. These 2-mode waveguide section here is where we do the modulation. So it consists of 2 silicon waveguides. And through this modulation, in the backward direction, we have this modal transition, photonic transition, between the even mode and the odd mode. So that if you have a fundamental even mode that comes in, you will couple to this even mode. And upon propagating along here, convert to the odd mode and radiates away. On the other hand, in the forward direction, the fundamental mode comes in, couple to the even mode, propagate, and then stay in the even mode and couple out. So in doing so, you will have a contrast in transmission coefficient between 2 single-mode waveguides. And that's perhaps the cleanest test of non-reciprocity, is actually to look at the transmission coefficient different in the single-mode, 2 single-mode guide. So on the electrical part, as I have mentioned, what they did is they have a waveguide consist of 88 independently modulated region, and each of them consists of p-n junction so that they do carrier injection, and the phase is then controlled individually on each individual section. So here is the experimental result. In the absence of modulation, what we did is we measured the transmission coefficient from left to right and from right to left. Now, this is a complicated structure, but the reciprocity will tell you that if you do not modulate, the left to right and right to left should have identical transmission coefficient. And indeed, that's what we see when we take the ratio between left to right and right to left transmission coefficient. Now, once you establish that, we turn down the modulation. As you do that, as you increase electrical input, you start to see a frequency range where you see contrast between forward and backward. And the frequency range where you see contrast is in fact far larger compared with the modulation frequency. This is a device that operates at 20 gigahertz modulation frequency, and the frequency bandwidth where you see contrast, even in this relatively unoptimized device, actually already exceed 200 gigahertz. So you could actually get very broadband response with a bandwidth that's much, much larger compared with the modulation frequency, which is, of course, one of the very important part of this kind of device. Now, one criticism one would say is, well, this seems like an enormously complicated device. You have to build a very complicated modulator with very difficult electrical control. And so one of the questions is, can we simplify it further? And that would connect to the second part of my talk, where we try to establish a connection between time reversal symmetry breaking for electron and time reversal symmetry breaking for photon. So I've shown you a very simple way to break time reversal symmetry for photon, and that is basically by a dynamic modulation with a spatial and temporal dependent modulation profile. Now, in electrons, usually you wouldn't obviously break time reversal symmetry this way. Instead, you will apply a static magnetic field. On the face of it, this looks like two very different concepts. But as I'm going to show, in fact, there's a very strong connection between these kind of concepts. The modulation, what it does is, in fact, it provides a gauge transformation or a gauge potential for the photon wave function. Okay. So to illustrate that, I will again go back to the photonic transition picture, but instead of considering an indirect transition where the two states that are involved has different wave vector, I'm going to be considering a direct scenario where the two states have the same wave vector, so you'll be modulating basically with only a time dependency, but no spatial dependency. So in doing so, obviously, you will induce transition between two states that has the same wave vector. And so if you start with one of the state, and then you turn on the modulation, you are going to see oscillation between these two states, as we have already talked about. Now, one interesting thing about this modulation, if you stare at it, is that we have actually arbitrarily set the modulation phase to be 0. Okay? And that basically says that we have chosen a particular time origin to measure the modulation phase. Now, the physics, of course, should not depend upon the choice of time origin. And so you can choose a different time origin. You will have a different modulation phase, but you should get the same physics. So indeed, if you actually would do this same kind of calculation, but now you use a modulation pattern with a slightly different phase, you will get an identical oscillation between these two states. And that's basically what the physics should have told you. But now what you have is a very interesting scenario. Now, what you see here is, in fact, a degree of freedom where you can arbitrarily specify the photon wave function. And that degree of freedom is a gauge degree of freedom. So in fact, this modulation phase here is precisely a gauge potential that couples to the photon. So let me start with this, again, with a simple example. Now I put in the modulation phase, and I solve the system. So I consider the system at any given time being the linear superposition of one of these two states. So in doing so, I can write down the amplitude of the state amplitude in front of these states, and you will get a 2x2 matrix govern this amplitude. And what you see is that the modulation phase here actually showed up in the phase of the coupling constant between these two states. And that's precisely what a gauge potential will show up. More specifically, what you come to see is that the upward transition and the downward transition now actually acquire different phase. Now, again, this being a gauge degree of freedom, this can be simply gauge away. But what you can do, if you need to see a gauge degree of freedom, is to construct an interferometer. So imagine that you have two sections of waveguide, and both of them you modulate, but now you modulate each individual sections with different phase. Then imagine that photon goes through a clockwise pathway, start with state 1, it go up here, propagate, and then go down here and goes back. Now you compare that with this time reversal pathway, where a photon starts here, propagate this way, go up here, propagate, and go down. You see that in the clockwise rotation case, it goes through an upward transition and a downward transition. Whereas in the counterclockwise case, it go a upward transition here and downward transition here. Now, these two pathways then will acquire these two pathways that are related by a time reversal operation would actually acquire different phase. So as a result, what you have is a phase difference between two time reversal related trajectory, and that phase difference come out of a gauge degree of freedom. And that's precisely a Aharonov-Born interferometer, but casted in a photonic setting. So as an implementation, you can imagine taking a silicon waveguide, modulate one part of the silicon waveguide, modulate another part of the silicon waveguide with a pi/2 phase difference. In this case, you can see that an even mode come in, get a complete modal conversion to the odd mode, and the even mode that coming from the right actually does not go through modal conversion. So we have actually simplified this very complicated modulator-based isolator down to two modulated sections, and in doing so, create an isolator based upon the gauge degree of freedom that came out of the modulation of the photon wave function. And in fact, we already have microwave experiment demonstrating this effect, and we are also very close in collaboration with Michael Lipson's group in demonstrating this in the optical frequency as well. Now, up to this point, I've shown you that you can use modulation to create an effective gauge potential for photon. So the natural next step is to actually create an effective gauge field for photon or an effective magnetic field for photon. So again, there are many effects, very interesting effects in terms of electron that you can do with magnetic field, one of them being a Lorentz force, and the other one being quantum Hall effect, as CT just mentioned. And being able to do so, create an effective magnetic field for photon, would then allow you to probe a very wide range of photon physics that you would not otherwise be able to do. Now, one of the interesting points, of course, about gauge field or a magnetic field is that that's intrinsically associated in the field theory with the charge of the electron. So there is no naturally occurring gauge field associated with photon. And so what we do here is in trying to synthesize a gauge field precisely for the photon wave function. And coming from the idea that we have talked about, the idea actually here is a relatively simple one. So keep in mind that the gauge potential here come out of a transition between photon wave function. So therefore, if you need to create an effective magnetic field, all you need to do is to imagine a lattice picture. So you will have a lattice that looks like this that consists of two sublattices. One of the sublattice is omega 1, and the other sublattice is omega 2. And then in each of the sublattice, in each of the bond here, you allow a dynamic coupling with a frequency corresponding to the frequency difference. When you do that, then by specifying the phase at each individual bond, you would then create a gauge potential distribution. So in doing so, in fact, this, once you do the rotating wave approximation and you rotate out basically the frequency difference here, you will get exactly the same physical model as an electron moving on a lattice subject to a gauge field. Now, in order to have two resonators and create a dynamic coupling between them, one way you could do is imagine two resonators that are spatially separated. For example, one of them having a dipole mode, the other one having a quadrupole mode. Now, to mediate the coupling, you put in an additional state in between that support a pair of dipole mode, one of the dipole mode in resonance with the monopole mode, the other dipole mode in resonance with the quadrupole mode. And in doing so then, driving a transition right at the intermediate resonator here would then allow you to couple these two modes dynamically with a phase then is associated with the modulation. So with this, now you, by specifying this phase distribution, and as I mentioned in the very beginning of this talk, in Michael Lipson's experiment, there is already a degree of freedom in the silicon modulator in specifying fairly complicated modulation in the phase pattern. So by specifying this, you could actually specify a number of effective magnetic field distribution. So for example, if you specify the phase on every single bond to be uniform, that corresponds to the case where the effective magnetic field is 0. On the other hand, if you choose this particular phase distribution correspond to what's called a Landau gauge, basically what you do is you specify in the horizontal bonds to all have phase to be 0, and the vertical bonds actually have phase that alternate from plus to minus, and then has magnitude that also varies in space. You could actually create a uniform magnetic field. So we know that one very basic signature of an effect of a magnetic field for electron is a Lorentz force. If you have an electron propagate against a magnetic field, and if the electron velocity is perpendicular to the magnetic field, it goes through a circle. So as a photonic demonstration, what we do here is we take a look at these two lattices. So half of the lattice here, we specify the phase distribution such that the effective magnetic field is 0, and the other half, we specify the effective magnetic field so that you have a constant magnetic field. Now, we initiate a constant frequency, but a field distribution that looks like this. It propagates in the uniform magnetic field region. It propagates, of course, straight. And then when it enters the field region with effective magnetic field, it goes around. So what you see here is basically a signature of an effective Lorentz force for photons. And one thing here, of course, is that now you actually have effective magnetic field that are completely controlled by dynamics. And you can specify the phase, and that would tell you what the effective magnetic field is. And so in this case, by changing the phase, you basically can specify different magnetic field strength. So for the same input velocity, it will actually go through circles with different radii, just as what you would expect out of an effective magnetic field. Now, the other very important effect about magnetic field electron is the quantum Hall effect. And this is a fact where you take a 2D electron gas and apply an electric field, a magnetic field perpendicular to it. And in doing so, you create a one-way edge state at the edge of the sample that are robust against disorder. And that's the argument of integral quantum Hall effect. In electrons, there also has been quantum spin Hall effect that have similar robustness. But now, given today, of course, in photon, it will be very interesting to be able to do the same thing, that you can create things that are robust against disorder. One of the basic properties of photon, however, is that it's a spin-1 particle. And therefore, it does not have what's called the Kramers degeneracy. In other words, the only way you can actually get a truly disorder robust edge state is to break time reversal symmetry. And that's where these kind of effective magnetic field concept actually come in to be very nicely. So as, again, a computer demonstration, we take a 20 by 20 resonator lattice. We specify the phase distribution such that it's subject to a constant effective magnetic field. We put a source on the edge of the sample. We oscillate the source. Now you can see that the radiation actually goes only one way, but it doesn't go the other. And that's, of course, a hallmark of a one-way edge state inside the system. And to see that this thing is disorder robust, what we do is we actually change some of the resonators to form a defect on the edge. And of course, the wave actually goes around it without backscattering. So you can see that you will actually be able to directly specify a one-way edge state in these kind of system without using magneto effect, but also have an effective field that are completely specified by dynamics, and therefore has enormous degree of freedom to specify these kind of gauge field. So with that, let me quickly summarize. So I talk about two things. The first part, I think, is a fairly practically driven research where we argue that it will be very interesting to replace magneto-optical isolator with dynamic modulation-based isolator. And this, in fact, is already becoming a reality, and we can do very, very well with this kind of isolator. The second part of my talk, I think, is more fundamental, is to say that these dynamic modulation are, in fact, quite interesting because it gave you an effective gauge degree of freedom inside the photon wave function. Moreover, unlike traditional magnetic field for electrons, here the phase degree of freedom can be almost arbitrarily specified, and that gives you an enormously different gauge degree of freedom that I think would be very interesting in terms of optical and electromagnetic physics. So with that, let me stop, and thank you for your attention. So this is, this is a imposed gauge field rather than a dynamic gauge field. So it does not have that particular aspect.
But if you have this symmetry somewhere, there must be something.
So it's very interesting to make this degree of freedom dynamic and explore it. And I think there will be actually a very interesting question about it.
If you have this, there's possibly another way of looking at this. If you have a spatial temporal modification, then you could imagine you're going into a frame co-moving with that modification. And then what you have is that your host medium appears to move against you. So this means if you apply a spatial temporal modulation, it's equivalent to having a moving medium. Now it's known that a moving medium corresponds to an effective magnetic field. And what you get is something like a version of the Fresnel of the Fizeau effect. So you have light or electromagnetic waves propagating with against the current or with the flow, and that of course does not obey reciprocity. So that's a possible another way of looking at it. It does not apply to your simplified scheme, but to the original one.
To the original scheme, I think there's certainly a connection.
But then you simplify that.
Right. Once you simplify, it's not obvious at all.
That's right. Yeah.
And also, I should say that it's interesting because obviously gyroscope, as I mentioned, use both effects. Use the modulation to bias it as an effective magnetic field, and then use the rotation, of course, give you the Zeniac phase shift, which is also non-reciprocal effect. So actually use both. Yes. The modulation scheme, the power of it, is that it gave you the degree of freedom to specify a gauge degree of freedom that are far richer.
When people talk about graphene, they talk about the two sites in the hexagon as the A and the B site, and make an analogy with spin.
Yeah.
And you have an A and a B site.
Yeah.
And I wonder if you could make an analogy with spin there. If you can, you then have, you can talk about it, and then you can put a magnetic field on that, effective magnetic field. Then you have something like the Raspar effect. And the Raspar effect comes about when you don't have time reversal symmetry. And I'm taking a long time about getting around to saying you can have a negatively refracting state there. What happens is that the dispersion of the bands cross at k equals 0 because they don't have to hybridize because spin is conserved, actually a conserved quantity. And as they cross, they transition from positive to negative refraction. It's a well-known effect in the Raspar effect for electrons. You do get this negative dispersion, but you seem to have invented it for photons as well.
So
Can you repeat the question?
let me repeat the question, but I probably will only repeat partially. So forgive me if I butcher your question already. I'm going to frame it in a way so that I can answer, obviously. So in graphene, there's a degree, even before the electron spin comes in, there's what's called the pseudo spin, which is basically the occupation of A side and B side. And exploiting that from a Barry phase argument, you could actually create an effective magnetic field as well. What we do here is actually quite different. Our scheme here is more closely related to the actual magnetic field. It's the pure substitution of the magnetic field on the square lattice. But obviously, certainly I think for photon, there got to be more than one way to specify an effective magnetic field. And I think that would be very interesting. The second part of the question regarding basically many of the complex spin optical coupling effects that in the presence of magnetic field that one come out in a graphene lattice. So I think it's interesting in this case to explore the graphene lattice as well, and we have not done that. And also to connect this with the orbital degree of freedom, the multi-level system, and the Barry phase associated. And we also have not done that. But I think there's tremendous richness in this.
So it's just fascinating. I want to talk with you in the break some more. But I'll just bring up the point about how magneto-optic isolators are used in real systems. And the purpose of the magneto-optic isolator is to prevent the laser from getting feedback from some reflectance that's way down the fiber that's completely out of control. And so if you think about that, the isolator that you initially described, it would just created a frequency shift. And it seems like you would have to have a very big frequency shift because the gain spectrum is rather broad. And so I was thinking of how you could substitute in a real situation. And it could be that by scrambling the phase, it wouldn't necessarily have to be exactly the traveling wave phase that you've introduced here, but some kind of scrambling that prevents the laser from getting feedback from reflectors that are way down the fiber. How do you deal? How do you really substitute for a real magneto-optic isolator?
So in fact, you don't need a frequency shift. So one thing that we showed is that if you take this device, you go from omega 1 to omega 2, right? If you make the modulation region twice as long, you go to omega 1 to omega 2 and omega 1 in the forward direction. So the same frequency and same mode. In the backward direction, you go from omega 1 to omega 1. But there's a phase difference. So you could get a non-reciprocal phase without any frequency filter, and that's important.
Look, it's non-reciprocal, but the omega 1 and omega 2 are close enough together
You do not,
that they would fall within the gain spectrum, and therefore you could disturb the laser.
Well, if you look at the actual thing that we did here, this is omega 1 in. So let me answer in two ways. The first is the point that I make. You do not need to do frequency shift. You can get a non-reciprocal phase and build a Mach-Zehnder and get a complete circulator that you would not know there's no magneto-optical inside. That's the first point. The second point is what we have demonstrated is that you can see the omega 2 basically get scattered away. So it's not in the waveguide. So if you
I think you're completely missing my point. My point is that you have a limited spectrum over which
you
this
don't.
works.
That's my point. You don't have that limitation. There is no such limitation. You do not need a frequency filter, and you do not need a modal filter. But I'll need to draw it to you. Okay. The second point, I think, is the use of isolator itself. It is certainly very important to prevent light to going back to a laser, and because that gives you laser stability issue. But what you come to see in many of the system design that people do is they throw isolator in whenever they have back reflection, even far, far away from the laser. And because you cut off the Fabry pearl, and you get a much better system. So from that perspective, it's not just an argument of protecting the laser itself. At least that's how I will argue.
Isolation by using nonlinearity.
Yes.
But I got an impression, I don't really work in this field, from a recent paper by my colleague.
Right,
Andy
right, yeah.
It's so easy, it's so straightforward. and it's so nice, simple structure, by far simpler than anything you showed. So why bother?
So that's a very good point. If you look at their data, their isolation region, first of all, they did a ring resonator, has very small bandwidths. And the second point, which is more fundamental, is that and they showed that as well in their paper, that there's only a range of intensity where you show isolation. And that fundamentally says that you have to assume something about reflection. Now, the point about isolation is to assume that the reflection is unknown, and you want to get rid of it. I think that's a very important point. In fact, if you know something about reflection, you do not need an isolator. And that's almost universally true. So the kind of isolator that we're talking about here, in fact, has a better performance in terms of many things, in terms of bandwidth and so on. But the fundamental point is that it's a device that can replace magneto-optical isolator. And any nonlinear device cannot.
With dynamic modulations, show us, you can create a gauge potential, for photon, when moving, it like if feel a magnetic field, effective. So Lorentz force,
right?
Like a charged particle, for
right.
electrons, for example. So my question, we know for charged particles when accelerating, it will, for example, there are some very interesting phenomena such as Cherenkov radiation. Right. So in your case, very similar to a charged particle. Is there any Cherenkov radiation for your photons?
There might. I haven't thought about it.
Okay.
There might. You can, given how complex the underlying band structure is, you may envision, and being modulated, the system being modulated, you may envision a frequency conversion with a Cherenkov-like behavior. Actually, that could be interesting. We actually have not explored it. That's actually interesting.
My second question is, in topological insulators, if you introduce magnetic defects, so you can kill the one-way propagation. In your case, you also break a time reversal symmetry. So what kind of defects can kill your one-way behavior?
So as I mentioned, for topological insulator, magnetic defect kill one-way edge state, or rather, the non-magnetic defect does not kill one-way edge state because the electron has Kramer's degeneracy. A photon has no Kramer's degeneracy, which means that the only way you can get a truly topologically protected state is by breaking time reversal symmetry. There's no other way around.
But you already did.
So in that sense, there's nothing you can do to break it.
Okay.
And that's the same as the edge state in integer quantum Hall effect. It's actually identical. I think this point I would really need to emphasize. People have done very nice work in one-way edge state in photon. But this is perhaps the first time that you can see something that's identical to the edge state in the integer quantum Hall effect.
So it's really integer, or you can show us, Or
sorry?
I mean, the transport properties is really integer, related to the integer behavior?
To integer quantum Hall effect behavior. In fact, it's identical. If you look at the Hamiltonian, it's basically a lattice Hamiltonian subject to a constant magnetic field. And that's precisely the model that gives you integer Hall effect, integer quantum Hall effect.
Very fancy jobs.
Right.
So looking at the time, it's time for our break. So we can continue the discussions there. And I'll close the session and thank all the speakers.
So it really is taking, you can do this by